Welcome to Math 201. This is lesson 5.4 on properties of definite integrals. The average value of a function. The value of a Tiffany lamp t years after 1965 is given by v of t equals 225 e to the point 1 t. And I've given a graph below. So here we have t, and here we have v of t, the value of the lamp. So I want to start by finding the average of v of 0 and v of 60. So that is the value at time 0, 1965, and the value 65 years later. What's the average between the two? So first I need to calculate v of 0 and v of 65 and v of 60. Okay, so v of 0 plus v of 60 over 2. That's how you calculate the average of two numbers. You um, add the two numbers together and divide by 2. So this is going to be v of 0, which is $225. So if you put in a 0 for t, you get 225 e to the 0, which is 225. And then if you put in a 60 for t, you get 225 e to the 6th. And we're going to divide that by 2, and we get approximately $45,498. Okay, so you can see that in 1960, it's like almost $100,000. Maybe it is, yeah, it's close to $100,000 in 1960. In, sorry, 60 years after 1960. At t equals 60, the lamp is worth almost $100,000. At t equals 0, it's worth $225. So the average between almost 100,000 and 225 is 45,498. Okay, so if I want to know the average value over those 60 years, that's a place I could start. But it spent more time having not a lot of value than it did being very expensive. So maybe I'll add another point, like maybe I'll do v of 30. I'll add that into my average. So now instead of averaging just v of 0 and v of 60, I'm also going to average in v of 30. So I'm going to do v of 0 plus v of 30 plus v of 60, 3 points, and I'm going to divide by 3, and that comes out to approximately 31,839. Okay, so the fact that this is lower is because there are 2 points that are pretty low and then only 1 point that has a very high value. All right, so what if I find the average of v of 0, v of 15, v of 30, v of 45, and v of 60? So I'm going to add a couple more points here. I want v of 15 and v of 45. That's not 15, but right there. Okay, so I would do v of 0 plus v of 15 plus v of 30 plus v of 45 plus v of 60, all divided by 2. Sorry, not 2. I'm going to divide by the number of numbers I'm adding, 1, 2, 3, 4, 5, divided by 5. And that gives me approximately $23,356 as the average value of the lamp over these 60 years. And again, that's because most of my points um, are closer to 225 than they are to this almost $100,000 value. So that's why these average values are coming down the more points I add. Okay, so I want to look at this graph and make our best guess about the average value of the Tiffany lamp over the period 1965 to 2025. That's a 60-year period. So I'm estimating the average of infinitely many values. So I got estimates for just the beginning and the ending value. I averaged those. Then I took a point in the middle and I averaged those three. Then I took a few more points and I averaged those in. And I'm gonna guess, so when I did the 5 points, I got about 23,000. So like here is my average value. I think that's probably a pretty good guess. I think maybe it's just a teeny bit lower. Um, my guess, maybe approximately 20,000. So we're going to find the average value of the lamp over the period 1965 to 2025. And it turns out that you need an integral to do this calculation because we're going to be adding up an infinite number of y values, an infinite number of points, and then dividing by n. So anytime you're working with an infinite number of something, what we're actually going to do is take a limit. And this translates to be an integral. So I'm going to do 1 minus b over a times the integral from a to b of f of t dt. So my average value is going to be 1 over b minus a, which is going to be 60 years, times the integral from 0 to 60. F of t is the valuation of the lamp, 225 e to the 0.1 t dt. So to evaluate, we need an antiderivative f of t. Um, so we need an antiderivative f of t such that f prime of t is 225 e to the 0.1 t. So I need an antiderivative of this function. So if I want to take the derivative of e to something, the derivative is e to that something times the derivative of the stuff, right? So this would be e to the 0.1 t times zero point 0.1. So I need to change this coefficient so that the 0.1, when I multiply by it using the chain rule, I get 225. So I'm going to need to add a 0 onto that. So we're going to use f of t equals 2,250 e to the 0.1 t. And then you can check me. Take the derivative of this and make sure you get 225 e to the 0.1 t. You should. All right, so I'm out of room here. I'm going to move to the next slide. Okay, so I've rewritten my integral for the average value. And to evaluate it, I'm going to use the antiderivative capital F of t. So this is f, oops, I forgot the 1 over 60. 1 over 60 times f of 60 minus f of 0, where f we said was 2250 e to the 0.1 t. So this is 1 over 60 times f of 60, which is going to be 2250 e to the 6, minus f of 0, which is just 2250. And I'll just put this in a calculator. I get about $15,091. All right, so why does this formula make sense? Let's apply the fundamental theorem of calculus. So 1 over b minus a, and then instead of the integral from a to b of little f of t dt, I know that I could use the fundamental theorem of calculus and evaluate that by doing capital F of b minus capital F of a. Okay, so this is f of b minus f of a over b minus a. So this is the average rate of change of f, capital F. And the average rate of change of f is the average of little f. Okay, so for instance, if capital F represents position, so this would be e.g. average rate of change of position. Rate of change of position is the definition of velocity. So this is average velocity. Okay, so the average rate of change of F gives you the average rate of change of big F gives you the average of little f. Here's our first activity for 5.4. Have you pause the video, try these problems. When you're ready to go over them, come back and press play. So a barrister is a small company which sells clothing items to youngsters in North America. When the new designs are released in January, the company projects sales of shirts, YFT, in units of a thousand per month. For the year 2021 is shown in the graph. We want to write an expression for A3, the average number of units sold per month over the course of the first 3 months of a year. You do not need to evaluate your expression yet. So A3 is the average amount of sales, average number of units sold per month. So that is the average value of this function over the first 3 months. So we're going to have 1 over 3 times the integral from 0 to 3 of y of t dt. All right, and then if I want an expression for the average number of units sold per month over the course of the full year, that would be A12, which is 1/12 times the integral from 0 to 12 of y of t dt. Why is the value of A12 less than 80? Okay. 80 is our sales per month in our busiest month of the year at month 6. In month 6, we get 80 sales per unit. Okay. Sorry, 80 units per month in June. Okay, but other times of the all the other times of the year we get less than that. Okay, so because average sales over 12 months should be lower than our peak sales of 80 units per month in June. Approximate the numerical values of A3 and A12 by using left-handed sums with a width of 1. All right, so I'm just going to rewrite A3 here. It was 1/3 times the integral from 0 to 3 of y of t dt. Okay, so from 0 to 3, I'm going to approximate this integral. So I have my 1/3. That's just this 1/3. And then I'm going to work on this integral from 0 to 3 of y of t dt using a left-hand sum width of 3. So I'm going from 0 to 3, breaking it into 3 parts. And my left-hand sum, that first rectangle has area 0. This second rectangle looks like it has area 5. Like that looks like it might be at a height of 5, base of 1, so 5. And then my next rectangle, that's definitely at a height of 20. And that's it. There's only 3 rectangles. So this is a third of 25 or 25 thirds. And then a 12 is going to be 1/12 times the integral from 0 to 12 of y of t dt. So that would be 1/12 times. Okay, I already have the first 3 rectangles drawn here. Their areas were 0, 5, and 20. And then I have to keep doing this all the way until I hit 12. So just draw in the rest of these rectangles. And it looks like those heights are, um, this one looks like it's about 40, and then about 60. They're doing real rough estimates here. And then this one might be 75 and 80 and 78. And see, this one looks like it's maybe 65. And then this one could be not quite 50, like 48. And this one looks like it's right at about 30. And this one's a little shy of 20, maybe 18. Okay, so I have 0 plus 5 plus 20 plus 40 plus 60 plus 75 plus 80 plus 78 plus 65 plus 48 plus 30 plus 18. Okay, and that comes out to about 43.25. All right, let's look at some properties of definite integrals. Thinking about geometry of areas should help us think about these properties. So the integral from a to a of f of x dx. So if I draw a picture of a function, the integral from a to a means the area between a and a, between the curve and the x-axis. But that has no width, right? There's no distance between a and a, which means it has no area. Okay, so that integral is 0. Okay, the integral from a to b of c dx. So if I draw constant function at a height of c, I'm going to put in an a and a b. This is just a rectangle whose base is b minus a and whose height is c. So this is b minus a times c. And then the integral of f of x plus or minus g of x is just the sum or difference of the integrals. So this is going to be the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. And then the integral from a to b of c times f of x dx. Just like with limits and derivatives, we can take this constant and pull it out of the integral. So this is c times the integral from a to b of f of x dx. Okay, then this last one, I have the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So here's my picture with a and b and a c in between. And the integral from a to c is this area. And the integral from c to b is this area. Okay, and if I add this pink area plus this green area, that would be the same thing as just taking the integral from a to b of f of x dx directly. And this actually turns out to be true even if c is not in between a and b. This still turns out to be true. What if the smaller number is on top? For example, what's the value of the integral from 2 to 0 of 6 dt? First, we calculate the integral from 0 to 2 of 6 dt. Okay, so this we know how to do. So here's 0, here's 2. My function is at a height of 6. So I'm looking for this area, which is 2 times 6, which is 12. Now we imagine that the integral from 0 to 2 of 6 dt represents the distance a runner travels in 2 hours if they're running at 6 miles per hour. And we can think of the integral from 2 to 0 of 6 dt as representing the distance traveled in reverse. Okay, so they would have gone 12 miles to the left, right? So the integral from 2 to 6 dt would be negative 12 miles. So in conclusion, we define the integral from b to a of f of x dx to be the opposite of the integral from a to b of f of x dx. Now, if f is even and I want to integrate from negative a to a, so here's, let's call this negative a and this a. So if f is even, we have symmetry about the y-axis. And I actually only need to integrate from 0 to a, and I can just double it because this area is the same as this area. So I can just do twice the integral from 0 to a of f of x dx. And if f is odd, here's negative a, here is a. This area is the same as this area, but the area on the left side is negative because it's below the x-axis versus the area on the right side, which is above the x-axis, is just positive. So these are the same areas, but this one's negative and this one's positive, so they add together to make 0. Consider the curves f of x equals x squared and g of x equals square root x pictured below. So let's label these. I have f of x equals x squared and g of x equals square root x. Find the area of the region bounded by the two curves. So that is the region highlighted right here. That is bounded by the two curves. It's between the two curves. And so it's between the two curves and it's bounded, meaning it's not infinite. So this area up here is also between the two curves, but those two curves keep getting further and further apart. So this is an unbounded region. Okay, so we want the bounded region between the two curves. So I need to know where they intersect. Okay, so I can tell from the graph that that happens at 1, but if I didn't have a graph, I would just set x squared equal to square root x to see when they cross. And I'd square both sides. I'd get x to the fourth equals x. So x to the fourth minus x equals 0. Factor out an x. And I get x equals 0 and x equals 1 are the two places where this graph crosses. These two graphs cross. Okay, so 0 and 1 are my bounds. So if I find the area underneath square root x, that's the taller function, I'm going to find all the area underneath square root x. Okay. And then I'm going to subtract off the area underneath x squared. So my area that I'm looking for is going to be the integral from 0 to 1 of square root x dx. And I'm going to subtract the area under x squared, 0 to 1 of x squared dx. Now my properties of integrals said that I can actually put these together into a single integral, the integral from 0 to 1 of square root x minus x squared dx. And this would be capital F of 1 minus capital F of 0, where capital F is going to be an antiderivative of this function. Okay, so capital F of x, I'll write it up here, would have to be, this is x to the 1/2, so it's going to be 2/3 x to the 3/2. And then the antiderivative of x squared would be 1/3 x cubed. Okay, so f of 1 is going to be 2/3 minus 1/3. And f of 0 is 0. So that comes out to 1/3.
We've reached the second activity for today's lesson, so please go ahead and pause the video, work through these problems, and when you're ready, come back to watch the video and go over them. Suppose that f and g are continuous and differentiable functions such that f prime equals g, and all of the following conditions are also true. Okay, for parts 1 through 3, find the numerical value indicated, and if there's insufficient information, we just write insufficient information. So the integral from 0 to 3 of f of 0 times g of x dx. So they told us that f of 0 is 5. So I can just put a 5 there. This becomes the integral from 0 to 3 of 5 times g of x dx. So this is 5 times the integral from 0 to 3. That's one of our properties of integrals, that if you have a constant multiple, you can pull it out of the integral. So 5 times the integral from 0 to 3 of g of x dx. And do we know the integral from 0 to 3 of g of x dx? We do. It is 12. So this is 5 times 12, which is 60. For number 2, again, I can replace f of 0 with its value. That's a 5. So this is 4 times 5. So this is the integral from 0 to 3 of 20 minus 1/2 g of x dx. So I can integrate each term separately, right? So this is a 20 minus 1/2 g of x. So I can integrate term by term just like I can with derivatives. So this becomes the integral from 0 to 3 of 20 dx minus 1/2 the integral from 0 to 3 of g of x dx. So the integral from 0 to 3 of 20, we could draw a quick picture to tell us how to do that. So here's the function 20, 0 to 3. It's just this rectangle, and the area is 60. So this is 60 minus 1/2. The integral from 0 to 3 of g of x dx, I know that is 12. So 60 minus 6 is 54. Number 3, we have the integral from 0 to 6 of f of x dx. So that is not listed directly up here. I don't have the integral from 0 to 6, but I do have the integral from 0 to 3 and the integral from 3 to 6. So I'm just going to add those together to get the integral from 0 to 6. So take the integral from 0 to 3 of f of x dx plus the integral from 3 to 6 of f of x dx, and that is going to be 4 plus 3, which is 7. So the reason we can do that is because I wanted the integral from 0 to 6. Okay, so that is the area under the curve from 0 to 6. If you know the area from 0 to 3, and you know the area from 3 to 6, then the area from 0 to 3 is just this area plus this area. From 0 to 6 is this area plus this area. So we can just add the two together and we have the whole integral. For number 4, I want the integral from 3 to 6 of f of x plus g of x dx. So I can break that into two separate integrals, the integral from 3 to 6 of f of x dx plus the integral from 3 to 6 of g of x dx. And those values are given. The integral from 3 to 6 of f of x is 3, and from 3 to 6 of g of x is not given. I'm going to have to figure that out. Okay. So, but 3 to 6 of f of x, I know that that is 3 plus something. Okay. So I'm going to figure out that something down here under the pink line. So I want the integral from 3 to 6 of g of x. What do I actually have? I have the integral from 0 to 6 and from 0 to 3. So I know 0 to 3 plus 3 to 6 should give me 0 to 6. So let me write that out. The integral from 0 to 3 of g of x dx plus the integral from 3 to 6 of g of x dx should give me the full integral from 0 to 6 of g of x dx. Now 0 to 3 I know is 12. 3 to 6 is what I need to know. So I have 12 plus something equals the integral from 0 to 6, which I do know is 7. Okay, so that means my question mark has to come out to -5. So this is a -5, and 3 plus 5 is -2. For number 5, I want the integral from 0 to 3 of the absolute value of f of x dx. I do not have enough information to do this, okay? Because f could have some parts that are positive and some parts that are negative on the integral from 0 to 3. I have no idea what f looks like. So here's 0, here's 3. I know that the net area is 4. So like this area minus this area gives me 4, but I have no idea what parts are positive and what parts are negative. So I can't do this without more information, a picture or a formula. So this is insufficient information. And then f of 6, I'm going to use the fundamental theorem of calculus to do this. Remember, we had this statement that f prime equals g. Said a different way, f prime is a function whose derivative is g. That's the definition of an antiderivative. So f is the antiderivative of g. Okay, so if I want f of 6, I could use one of these integrals that has 6 as a bound, with g in it. So maybe I'll use this one, the integral from 0 to 6 of g of x dx. So the integral from 0 to 6 of g of x dx. If I use the fundamental theorem, I could use an antiderivative of g, which would be f, and I would do f of 6 minus f of 0, and I know that that's going to equal 7 because I know the value of the integral already. Okay, so maybe I'll write that down below. So I have 7 equals f of 6 minus f of 0, which was given as 5. So I add 5 to both sides, and I get f of 6 is 12.